By now, you've probably seen some of the amazing images from the James Webb Space Telescope. They're awesome. Now, I recently got the chance to talk to Dr. Randy Kimble. He's one of the project scientists for NASA and for the James Webb Space Telescope. He's been working on it since 2009. And what we're going to find out in this interview is a little preview of what's to come.
Well, it's a very exciting day, not just for astronomers, but for anyone in the public who's interested in how the universe works or interested just in appreciating the beauty of the universe. And the observations that were released today, which I remind everyone came from just 5 days of observation time with this amazing observatory, they really cover a wide range of the kind of science that Webb will be able to do. Starting closest to home, we looked at the atmosphere of a planet orbiting another star. That's a very different planet from Earth, a really hot, steamy one, but you could see very clear signatures of water vapor in the atmosphere of that planet. And we'll be studying many other exoplanets, including some that are much more like the Earth, and very interesting to see what their atmosphere compositions will be. The images also studied the processes of star formation, that Carina Nebula image, where you see the formation of stars in clouds of interstellar gas and dust, and infrared is great for penetrating the dust and seeing processes that would be completely blocked and hidden from you in visible light. So the IR capability of Webb is spectacular for that. And then going farther, we also saw star death, planetary nebula shedding the outer layers of a star, recycling that material into new generations of stars in the galaxy. That's really cool. I personally like the extragalactic stuff a lot. And we saw interacting galaxies in a tight cluster where the galaxy's gravitational dance is tearing tidal tails off, ripping streams of stars out, shocking gas clouds, making new generations of stars. So that's really cool. And Webb's very sharp vision and wide wavelength coverage is great for studying that system. But my personal favorite is the deep field work. And so that was the deep field image, which in only half a day of exposure time is the deepest infrared image that has ever been taken at those wavelengths, meaning we can see fainter objects than we ever could before. And that really is related to the initial science driver for Webb, of seeing the first stars and galaxies in the history of the universe. And it's that kind of deep field image that probes that early epoch best. And so it's not the big foreground galaxies, which are cool in their own right, but some of those little red things in the background will be found to be very early objects, only a few 100 million years after the Big Bang.
Yeah, very close to after the Big Bang, which is really amazing in that. So when we're looking at the deep field image, what direction, or does it really not matter so much, but what direction is James Webb looking out from the solar system in perspective from that?
I don't even know where exactly that field is, because what's remarkable is how rich the universe is. That field with thousands of galaxies in it, that represents an area of sky that is about 1% of the size of the full moon. It's less than 1%, in fact. And picture how small the full moon is compared to the whole sky. So there are an unbelievable number of galaxies in the universe. And as long as you get away from the light of our own Milky Way galaxy and get away from the light of the interplanetary dust in the plane of our own solar system, it doesn't much matter where you look. There are that many galaxies everywhere. So you pick a region where there aren't bright stars to distract your view. And if you take a deep exposure like that, you will see thousands of galaxies anywhere you look.
It's kind of interesting to think too, because part of the view looking out is blocked by our own Milky Way.
Yes, you don't want to try to do extragalactic work through the 100 billion stars in the Milky Way. So you don't want to look right through the plane, but as long as you look at high galactic latitudes is what it's called. And then, as I say, away from the brighter parts of the solar system, you can do that kind of extragalactic deep field work anywhere.
I had a question from a viewer. What is kind of just a simple way to describe the resolution difference that we can expect between the James Webb Space Telescope and Hubble?
Webb is several times larger in diameter, and the diameter of a telescope's mirror is what sets its angular resolution. That places a fundamental physical limit on how sharp an image you can make. And because Webb is about 2.5 times, even a little bit more, the diameter of Hubble, it means you can get the same image sharpness as Hubble at 2.5 times longer wavelengths. Or put another way, when they observe at the same wavelength, Webb's image would be 2.5 times sharper in each dimension, which is 6 times more resolution elements across the face of a small galaxy or nebula or whatever you're looking at. So it's very sharp, and it gathers huge amounts of light with that big mirror, and gives unprecedented sensitivity for any kind of astronomy that you want to do.
There's going to be a lot of things that we're going to learn from the James Webb Space Telescope. And another question from another viewer as well was asking, are there any questions that we've always wondered about astronomy and about exploration that we might learn from this, or what things we might learn? For example, understanding of dark matter.
That's pretty tricky, but those extragalactic observations, when you put a lot of statistical studies of galaxies together, you gain information about dark matter. Direct detection of it has eluded people so far. We still don't know exactly what it is. What I personally am really interested in is that early epoch of galaxy formation. I think that's a fundamental question that people have. We see all these spectacularly beautiful galaxies around us. How did they get started? And the analogy I make, we've kicked around the number today that, we're looking back more than 13 billion years. And some people may remember, I thought Hubble looked back 13 billion years. What's the difference? And what matters is not that, it's a few 100 million years out of 13 billion. What matters is how much closer to the beginning that you're looking. So the analogy that I've been making today is, if you want to study human development, you can look from old folks like me to, say, kindergarten age people. And that's a very interesting history of human development. But there's a whole lot that goes on before kindergarten back to infancy. And with Webb, we want to take those steps. We want to see toddler galaxies and infant galaxies. And that will tell us a lot about how the early structure of the universe evolved. And that's going to be really exciting.
That is going to be really exciting, because there's a lot of things that we don't even know what questions we're going to have after we've studied what we're going to study with this telescope.
For sure. That has been universally true over the many decades of astronomy and astrophysics, is when you develop a powerful new observing capability, you go off and study the things that you knew to look at. We know we want to look at early galaxies. We know we want to look at these exoplanet atmospheres. You do all kinds of stuff that you have some idea what to expect. And then you say, whoa, what was that? And you learn some new phenomenon that is worthy of follow-up. And so any new observational capability like this always raises new exciting questions to explore. That's one of the great things about science, is there's always more to understand.
I'm sure you've been holding your breath for a long time with all of these milestones that you've had to get through since you first started working on it back in the late or early 2000s, 2009 till now, and after the launch. So congratulations once again, Randy. Thank you very, very much for your time today.
Thank you for having me. Go Webb.